Good evening, everybody. Thank you so much for joining us and welcome to the May SAGES Stories event, The Science of Climate Predictions. My name is Graham. I'm going to be your host for the evening. Just going to do a couple of housekeeping things while we hopefully any latecomers come onto the call. We're going to have questions later at the end of the talks. So if you want to ask any questions, there's a little Q&A box at the bottom on your right. And if you've got any problems throughout the talk, you can ask for help in the chat box, which is at the bottom, just a little bit to the left. We've got the lovely Hannah again, lurking in the background, who can help you if you have any problems this evening. Also, just to let you know, the session will be recorded and it will be made available on the SAGES YouTube channel after the event. But don't worry, none of your names or your faces are going to appear in the recording, just our lovely panelists. So just as a little bit of an introduction to SAGES, the event is hosted by the Scottish Alliance for Geoscience, the Environment and Society. Now, SAGES is a pool of researchers from institutions all across Scotland who are working on a range of environmental and socially relevant topics. And as we've seen in the last few events, if you've been able to join us, SAGES has a number of themes and forums, which are basically groups of researchers working together on similar topics. Now, this month, we're focusing on the Centre for Earth System Dynamics. And scientists in this group are working to observe, model, and predict how the oceans, how ice, land, and the atmosphere are interlinked, and trying to understand the physical processes. Working together in this way allows scientists with different skills and different backgrounds to view the Earth as one coherent system, which is as much an important philosophical outlook as a scientific outlook these days. Now, this is the fourth event in the SAGES Stories event series, which is being held in the run-up to COP26, which, if you don't know, is a big climate conference being held in Glasgow at the end of the year. And these events are all about the excitement and the challenges of finding scientific solutions to climate change. And the events series spans the globe all the way from the Arctic to the Antarctic, trying to engage you, the public, with the work going on today. So if you'd like to find out about future events, and let's face it, why wouldn't you? You can sign up to the mailing list and the link will be in the chat at the bottom. Now, just a tiny minute about the structure of the event. We're going to have 4 short talks from 4 amazing speakers this evening, and then we're going to go into a discussion and a question and answer session. Please do feel free to write some questions in the box, as I said, at the bottom on the right. Yes, and we'll get to some of those questions at the end. So, without further ado, I'm going to introduce our first speaker. So the first speaker this evening is Sabine Undorf from the Department of Meteorology at Stockholm University. Originally from Germany, she completed an MSc in Glasgow and apparently loved Scotland so much that she came back to do a PhD in Edinburgh in atmospheric and environmental sciences. Now, she's interested in quantifying climate change from the time of industrialization right into the future. And she's recently worked with various stakeholders on climate change adaptation in Scotland and even helped to develop a board game to use as a scientific tool. Her current research focuses on characterizing the uncertainty in future climate projections, as well as looking at society, ethics, and climate change as a whole. And living in Stockholm, she tells me now she misses the cozy Scottish pubs, which is something I think we can all relate to right now. So, Sabine, would you like to begin your talk?
Absolutely, thanks for the nice introduction. I'm trying to share my screen, which you should be able to see now. And yes, so I assume presentation mode is not doing anything. Maybe this is okay anyway.
Yeah, I can see it fine.
Yeah, it's not quite full screen, but it's only getting worse.
It was fine, Sabine. It looked good. No problem.
Okay, do that again. Okay, right. Okay, so here we go. Right, yeah. So talking about climate change, and I guess you're interested in that because you're here. But sometimes it might feel a bit far away in the future or in space. So I'm going to start by talking about climate change in Scotland. And one thing you might even remember is summer 2018, where it was warm, so there was a heat wave. So on the left you can see a map, and you basically see it was warm everywhere, including in Scotland, and especially in southern Scotland. Temperatures reached the high 20s, which you will know from experience doesn't happen all the time. Especially because this is showing a 5-day period, so it's 5 days in a row that were so warm on average. I remember that I went cycling in June, and that was really nice. But we looked at the impacts of these heat wave and take the next slide. Yep, and here you see a bunch of headlines from the news over this time. We did a bit more quantitative.
Sabina, I'm really sorry to interrupt you, but your
Yes?
slides haven't changed, I don't think, for the audience.
I'm sorry for that. Oh, this is really annoying.
Okay, you're talking about a very exciting map that we'd love to see. So,
oh no, can you see it now?
nope,
I
sorry.
stopped share and start sharing again.
Yeah.
Oh, really sorry, everyone. It worked a second ago when we practiced this.
Great, I can see a heatwave map.
Perfect.
Now you can see heatwave map.
Great,
Okay.
yeah.
Right. Okay. So that was talking about that it got quite warm in the late 20s, to the high 20s in degrees of Celsius. If I now go to the next screen, can you see a new screen? A new slide?
Yeah, that's
Yep.
perfect.
Yep, perfect. So this is the headlines I was talking about, where you can see impact. Some of them were positive, like more ice cream was sold, but quite a lot of them was a negative. So many had to do with drought that came with the heat, including agriculture and more generally water stress, and also infrastructure failure. So allegedly the science center roof melted a bit, but also in transport, where impacts lasted quite a while, quite long into the year, including to Christmas. And there's also impacts on the whiskey industry that were even longer that are not on here. So, okay, it was hot and that had negative impacts. So what? It's just weather, is it not? Well, we looked at that. And if you look at the historical, can you see a new slide?
Yep.
Yep, it's all working fine.
Sorry, this is annoying. Okay, so if you look at the historical context, so you can see this was quite unusual in the climate of the 20th century, at least in the second half, even there. So how unusual depends a bit on what you look at. So if you look at a whole warm month, or if you look at a 5-day period, as I was doing, or at the single hottest day. But for instance, for the warmest night, it had a return period of something like 35 years, which means that in an average summer from 1950 to 2020, you would have expected this once every 35 years. But of course, in that period, there's already climate change in there. So in the second part of the study, we did an attribution. So we looked at whether climate change so far has changed the likelihood of this event, and found that it had done so significantly and made this more likely. And now looking at the future, these events are projected to become more common as well. So to the right, you can see two graphs that show climate projection from the Met Office. And so you see for each of these plots, you see two different colors. So that is two different sets of projections, a newer one and an older one. They're quite different in terms of emission scenario and the climate model used. That's not so important now, but you might take this as a part of the uncertainty in this. So both of them might plausibly happen. And what is shown here is that for time from 1980 to 100 years into the future, from then, the likelihood of any year to have, of any summer to have a period as warm or warmer as observed in 2018. And especially for these nighttime temperatures compared to the daytime temperatures, you can see that they've already become more likely, so I was saying before, but they're projected to become a lot more likely in future. And so much that towards the end of the century, we have something like 100% here, which means that every summer would on average be expected to be as warm or warmer. Which then means that we should adapt to this to alleviate some of the negative impacts and maybe even make use of the positive impacts. And assume that you can see a next slide where that says climate change adaptation, which is that is then about. And in order to do that, we have to know how climate is changing, of course, but that's not enough. We also have to know what impacts that has and how we can deal with them, so how we can reduce our exposure and vulnerability to these impacts. This is a photograph taken from a project we did with infrastructure stakeholders in Scotland, where we got them talking about how they can and should adapt to extreme events, including heat waves, but also floodings and storms, etc. But so here, so we're climate scientists, so we talk about how the climate is changing. And in Scotland, Met Office projections are telling us that the summers are becoming warmer and drier, shown on the left, and that the winters are becoming warmer too, so they become milder and wetter. There's a lot of things in here. I just want to point out the different colors of the dots. And that is, so the blue and the yellow ones are results from climate models, from global climate models, and then you can downscale them to arrive at more regional local information. So we need the global climate models, where we talk about later, for such projections. Based on this and other evidence, the Met Office then derives at these assessed ranges, which is the black range here. Another way in which climate change manifests in Scotland is more intense and heavy rainfall events, leading to flooding both in summer and winter. And the last thing I want to talk about is sea level rise. So here you see again such a plot where you can see the time on the x-axis, but now the different colors are different emission scenarios. And this is telling sea level rise in Stornoway. So you can see there's quite a lot of uncertainty. So these ranges overlap quite a bit, but there's also quite a big difference between what is here the highest value we might likely achieve, given this emission scenario, something between 50 centimeters or a whole meter, which might well have imply big differences for what that means for Stornoway. And I forgot to say, so we talk about global warming, but really, as I've shown you, it's not just about warming. It's about lots of other aspects of climate too. So I've talked about adaptation, which is important because climate change is happening and will be happening more. But this by no means means that we should not stop emitting, because adaptation has limits in Scotland and elsewhere. So this needs to be complemented by emission cuts. And especially if we go more into the future, you can see that whether we are on the blue scenario and the red scenario makes a massive difference for what's happening, what climate we have in the future. Even though this is uncertain, we do know that this makes a difference. So I'm really excited for COP, and yeah, and for the next talk, when Massimo will tell us about how we derive at these projections.
That's great. Thank you so much. And thank you for introducing the next speaker. We're going to go straight to him now. So next up is Massimo Bollicina, a senior lecturer in atmospheric sciences right here in Edinburgh. Now, he originally studied physics and has carried out research in Italy and the USA before moving here to Scotland. Currently, he studies the mechanisms of climate change and its variability at a regional scale. And his day-to-day work includes teaching, supervising, and collaborating with international research institutions across the world. And my day-to-day work seems to just be more drinking 4 cups of tea in a row. So there's a bit of difference there. And after all that work, when he's got spare time, he likes running and hiking in the mountains. So before he runs away up a Monroe, I'd like to hand you over to Massimo.
Thanks, Graham. Here we are. Is it shown correctly?
I can see it. Lovely. Thank you.
Okay, thank you. Okay, so hi, everyone. So the question that I want to address is, how do we as climate community make climate projections? And just to give a framework, just to remember, we talk about climate models, so we have to talk about the climate system. And when we talk about the climate system, we have to keep in mind that the system is composed of 5 main components that we see here: the atmosphere, the land, the ocean, the ice, and the biosphere. And they are all coupled by coupled processes and mechanisms. And plus we have the human imprint, which is shown here as industry. So in a climate model, we try to represent all these processes and mechanisms by which the various components interact. And we need a climate model to provide quantitative information on the climate system. And so why model? A model is, from simple to complex, is a selective representation of a phenomenon of interest. Selective because we choose what we put in the model and the extent to which processes are represented in the model. And how do we use the model for? What do we use the model for? There are various uses of a model. We can use it to predict or project the future. Bear in mind the two terms are actually used sometimes as one instead of the other, but they are different. We can use the so-called sensitivity experiments, which are shown as the second point. So what if a certain phenomenon, a certain component is switched off? And these are some examples. We can use the model to compare with observations and try to understand which aspects need to be included in order to explain the observations. And finally, to understand the mechanisms underpinning a certain phenomenon. And again, to try to disentangle aspects that in reality we cannot do. We have just one realization of reality. We can run the model how many times we want to some extent. So how is the model? What is the model? What is the core of the model? A core of the model is a set of mathematical equations that represent the balance of key quantities at various points in space and how the balance varies in time. Quantities include temperature, humidity, mass of air, and so on and so forth. And these points are actually points, because we cannot solve the equation for every point in space. Points are actually representative of sort of cubes, three-dimensional cubes around those points. And we have the distribution in the vertical as well as in the ocean, as shown in the bottom left figure. And the balance varies in time, of course. And we have a set of sources and sinks for which for this quantity, which, as I said, can be temperature, can be humidity, and so on. And the model also takes into account the distribution of land, the ocean, the elevation of the mountains, the ice, the input of solar radiation from space, and so on. So we solve this set of equations, balance equation, for every point in space, and we have a 3D distribution of points. As I said, we have sources and sinks. Some sources and sinks can be directly resolved by the equations in the model. Some others can be only statistically represented in the model. This is because either they are too complex or unknown, or they occur at too small scale. This is the case, for example, of clouds that involve, as you see here, representation of a thunderstorm. We have updraft, we have downdraft, we have entrainment of air from the surroundings. We have a lot of processes going on here, and many of these we don't know, and many of these can only represent it in terms of mean quantities over large scales, not really micro scale as the cloud assumes. And given all of this, you wonder how the model is, how do we make these predictions? And running a climate model is quite a demanding exercise. This is why we need supercomputers, and 3 of the main supercomputers in the world are represented here. This is the Met Office, this is Cheyenne from NCAR, bottom left, and to the right is the new supercomputer that is being installed here in Edinburgh. And typically, climate models take about 1 or 2 days to simulate several years. It takes about 1 month to simulate 1 century long. So, for example, if you want to simulate the 20th century climate with one realization, it takes about a month. And just to give a quantity, the new Archer 2 supercomputer that is being, as I said, ported here in Edinburgh, will have a full performance of 28 petaflops, which means 28 quadrillion operations per second. And it's news now that the Met Office has signed a contract with Met Office for 1.2 billion pounds to basically have one of the top supercomputers in the world for weather and climate. And so how do we make use, essentially, of this power? And the more cynical of us can say, how do I make use of this money? And here it is. This is I may ask you, is this a model or this is reality? This is actually a model, is a very high resolution simulations of water vapor at hourly time scale over the world. And you see here some features that you might know already, some others might not be known to you, but this is actually very consistent with reality. This is the state-of-the-art climate modeling now. And so models, how do we have reached the models that we have now. It has been a long history that started in the 50s, in the 60s, and the first component that actually was created was the atmosphere only. We live in the atmosphere, so that is the key component that we started the models from. And then from time to time, we added different components. And in the 80s, we coupled the atmosphere with the land surface. Then we added the ocean in the 90s, and so on and so forth. Notice here that the carbon cycle, which is very important to understand the future of our Earth, as we have sources of sinks of carbon, and actually is being added in the 2000s, as well as full atmospheric chemistry, added again in the 2000s when we include all the processes and the pollution-related processes. In terms of IPCC, the Intergovernmental Panel of Climate Change jargon, we had the first assessment report, second assessment report, and so on and so forth. And so you see here the time scale. In the 90s, we had the first report, and the second, and the third, and the AR4. And model development also included an improvement of the horizontal as well as vertical resolution of the models, as shown here. Again, we moved from models that had the resolution of a few hundred kilometers in grid boxes, as we saw before, those cubes, to models that now have a resolution below 50 kilometers in space. So that's quite a huge improvement, and of course, a huge demanding of computational resources. So how do we run model? To run the model in the future, we have to have drivers. Otherwise, how do we make predictions? And this is why we use now the future projections of emissions. And these are based on the socio-economic pathways. And these are different from previous efforts doing these predictions because these scenarios are built on assumptions on socio-economic development integrated with pathways of emissions of greenhouse gases and aerosols and so forth. So we have this trajectory for the future, and these are represented here. The top panel shows the future emissions of greenhouse gases, and we have different assumptions that, of course, lead to different pathways and more or less optimistic future scenarios. As you see here, the worst is the purple one, and the best is the green one, as well as these are greenhouse gases, and the bottom one is emissions of sulfate, so coming from industrialization, industries essentially. So this is related to pollution. But of course, as you see from the spread of these curves, we have a number of scenarios, and depending on which trajectory we'll follow, the climate will change accordingly. But from drivers, we reach two outputs, okay? And so this is a quite complex figure, but you don't have to go into details. What's the key point here is these are projections or simulations of winter temperature trends over North America or trends over 40 years, and done with the same model, but simply changing the initial condition. Why we need to run when we have to have different initial conditions in the model? Why we have to run the model many times? Simply because initial conditions are not known perfectly. We cannot measure every point in the atmosphere with certainty. And second, because the climate system responds to external drivers, which can be emissions of greenhouse gases, but also has internal variability. And we'll see Joanna that will touch on this point. So therefore, internal variability means that processes are coupled in the climate system, and they vary, they induce oscillations that vary by themselves. So regardless of how emissions of greenhouse gases vary. You see here that the model run with the same model with same drivers actually leads to different patterns and magnitude of temperature change over the United States. And this goes into projections, and the right maps show this temperature anomalies, time series of temperature anomalies, and you see the spread around each of the curves represent indeed ensembles, so the different realizations of the same model. We have to sample this variability in the initial conditions and in the climate system. And not surprisingly, the models differ, and the bottom panel shows indeed the different climate models and how they respond to the same forcings and how they produce the temperature trend. You see that the same model to model produce different trends, different magnitudes, and you see a spread. For example, if you look at the brown points, they represent different models, and you see some points produce trends of 0.3, 0.2, some others produce trends of 0.1 or less. So there is a spread of this model. The model different by the physical processes that are represented, how the processes are parameterized, are represented, the resolutions, and so on and so forth. We need essentially to have different realizations with the same model and different models in order to sample and to make climate projections. And models are not perfect, they have biases. And this is one typical example, the simulations of precipitation over Asia, which is associated with the Indian monsoon. The top panel the top figure shows observations, and then the middle row shows four different groups of models, and the bottom row show the biases. So the difference between the model and the observations. These are state-of-the-art climate models. As you see, the third panel shows orange colors, which means that the model shows a drier bias, while the right panel show mostly blue colors over India, which means the model overestimates precipitation. As you see the magnitude, actually the magnitude of the bias in some cases is comparable to the climatology of the model, which means that the bias can be quite severe. Okay, so there are uncertainties. And so just to conclude, models are based on physical laws. Models are able to simulate important aspects of current and past climate, but the model is still an hypothesis and include parameterization, which means they have tunable parameters. There are some uncertainties in the models. We have seen uncertainties. I touched upon the uncertainty associated with clouds. Of course, if we go to smaller scale, there are uncertainties in projections because we go to regional scale. There are interaction with internal variability of the system, internal variability and modes of variability. You certainly have heard about the North Atlantic Oscillation. There are uncertainties also in physics that goes into the model associated with pollution-related particles. And there are uncertainties associated with the ocean coupling. Also because, Joanna will talk about this, observations in the oceans are limited to the last 30 years or so. But I want to leave you with a twist. Models are not perfect, but what about observations? Observations are not perfect either. So we need to validate the model with observations, but observations are not perfect. This time series shows the time series of monsoon precipitation over India. And so you see that the yellow circles, actually, these are observations. You see that observations deviate one from another in the last 10 years or so, surprisingly. So this means that observations are also uncertain. So when we compare the model to observations, we have to keep this in mind too. Thank you.
Thank you so much, Massimo. And we're going to move on from learning what climate models are to learning about what we can see in the past. And we're going to do that with Andrew Shearer. He is a Chancellor's Fellow at the School of Geosciences in Edinburgh, and he's completed a PhD in astrophysics at CISA in Trieste. Andrew's interested in understanding the causes of climate change in the past, and especially the effect of natural variability, and then compares past observation to complex climate models today. Like Massimo, in his spare time, he's also very into hiking as well as travel, and I would like to hand over to Andrew now.
Thank you. I think I'm trying to share my screen. Can you see my screen?
Not quite yet. I'm sure it's on its way.
Up to, is it? Oh, can you?
Yeah, it's coming up now.
Sorry about the delay. I can't go back. Oh, there we go. Can you see the first slide?
Yeah, that's it.
Wonderful. Sorry about that. Okay, great. Well, thanks, Massimo, for that excellent introduction. So that was a very good discussion about what a climate model is and how, so it forces me to talk about a little bit more about how these climate models can be used. One important application, of course, is to compare the outputs to observations of past climate, to learn about the causes of past climate changes and also to see how well the climate models are doing. So, of course, we are now continually monitoring many different aspects of the climate, building up a wealth of data on a huge number of different variables. However, when it comes to long-term records, the best and longest by far is almost certainly temperature. The thermometer was first developed in the 16th and 17th century, and measurements have started to become widespread from about the mid-19th century. These observations have been made in ships by water from buckets, or more recently from engine intakes. And they've also been taken over land by thermometers and specially designed screens. However, particularly early on, there was very limited spatial coverage, and also there were changes in time in the way these measurements are taken. For example, using standard buckets, then canvas buckets and insulated buckets, as shown here. And this presents a whole host of problems when it comes to combining them all into one data set. As first, you have to overcome some of the different biases. However, the figure on the bottom of this slide shows the answer obtained by different groups working on estimating global temperature from lots of different climate centres. And as you can see on this figure, reassuringly, all of them come up with very similar data set estimates for this is global temperature. They all show the same kind of patterns. They clearly all show a warming over the 20th century, albeit with periods of faster and slower warming. For example, here and then slow. Recently, the slower warming in the first part of the 21st century received some interest and was often referred to as a hiatus. However, seen in the context of the past 170 years here, it is quite clear that global warming never stopped, as some claimed at the time. So we can now use the climate models that Massimo was talking about to see if we can match this temperature record. This involves getting an estimate of both how the anthropogenic drivers of climate change, such as greenhouse gases, aerosols, and land use changes have been changing, but also importantly, as well as changes in natural drivers of climate change, such as volcanic eruptions and solar variability. And these drivers of change are usually referred to as climate forcings, and will be throughout this talk. So in order to do this, we get our best estimate of all the forcings we think are important, and we put them all into a climate model and see what the answer is. And this figure illustrates this here. So the observations as shown before, again, the global mean temperature are shown in black here, and the orange browny color with this shade here is showing the climate model outputs with all our forcings that we think are important. And as you can see, the black line falls nicely within the uncertainty range of our models at all times. And this shows that we're doing quite a good job of capturing the important processes. We can also run climate models with combinations of these forcings. For example, in the green line, our climate models just run with natural forcings. And clearly, this green line cannot match the changes we observe in black. And this can be shown in a more rigorous way by using statistical techniques. Instead, the observed warming could be explained by a combination of an increased warming shown by greenhouse gases in grey, offset by cooling of anthropogenic aerosols in blue. And these are tiny particles of pollution which reflect the incoming solar radiation. So that's the past. So that can be used to learn about the causes of change, and also give us some idea about which models are performing well. In a similar way, we can also model the future. And this is more complicated, of course, as Massimo said, because we do not know what the future forcings will be, as they are dependent on how humans act. Instead, we can create hypothetical future scenarios of worlds in which humanity acts in different ways. And for each scenario, can calculate how humans will affect different parts of the world. So how one of the most important forcings, emissions of carbon dioxide, is predicted to vary under these different scenarios is shown in this figure. And as you can see, these scenarios cover quite a range of possibilities. For a world where we start rapidly reducing carbon emissions, to one where we keep on increasing carbon emissions into the future. And so these and other similar inputs, such as change in agriculture, can be put into the climate model, and the consequences of our actions can be calculated. As you can see from this figure, this shows both the highest forcing scenario and a more gradual one. And you can see there's a massive spread of uncertainty. These models show global temperatures warming by the end of the century by a fraction of a degree, by nearly 7 degrees. And if you want to understand where this uncertainty comes from, we can break it down into its separate sources, as shown in this plot here, where on the left, this figure is showing almost identical information before, albeit with a different color scheme. And on the right, this breaks down the uncertainty among these different lines to these three sources of uncertainty. So the biggest one, at least for global temperature, is coming from the scenario uncertainty. That's the uncertainty in how humans will act. And of course, we cannot do much about that. We can just hypothesize different scenarios. But there is still a considerable uncertainty in blue. This is the model uncertainty, which Massimo was touching on in the previous talk. So this is the uncertainty. So even if two different models run using the identical scenario, they come up with a different answer about the future. And this is the uncertainty that that scientists are really working on now to try and reduce this uncertainty by improving climate models. Also on this plot is a third source of uncertainty, and that's internal variability, which can be thought of as chaotic weather. This part is unknowable in a similar way to the fact that we cannot know what the weather will be like in the coming days. Although this is unknowable, because although we know what the weather can be like in the coming days to weeks, we cannot know what it will be like in 40 years' time. So although relatively small on the global scale, this source of uncertainty, internal variability, can be quite large regionally. And Joanna will discuss this topic more in the next talk. And finally, I'd like to stress that although everything I've shown so far has been focused on global temperatures, this of course is not what people actually feel, which is the climate locally to where they are. And the effects will not be uniform everywhere, with some areas, in particular high northern latitudes, warming much more than others, with the warming much larger as the global mean increases. Potentially even more important than warming is the fact that the hydrological cycle will change as well, with some places getting much more rainfall, and some areas, such as the Mediterranean, much less. And as you can see from the colour bar, some of these changes are really quite large percentage of the total rainfall, so will have huge impacts. So I just want to conclude there and summarise. Climate models can be used to learn about the past and what the future might be by driving them with the different estimates of climate forcing. But the resulting climate projections are not all identical and are dependent on both the choices humanity takes and the choice of models used. So how we choose to mitigate climate change or adapt to it must carefully take this uncertainty into account. Thanks.
Thank you so much, Andrew. You mentioned chaotic weather, which I feel is just what happens when we live in Scotland, to be honest. Thank you. So we're going to have one more speaker tonight. Just before we move on to her, I just wanted to remind you that there is a Q&A box down. I think I might have said both right and left. So it's down at the bottom, hidden somewhere. Do feel free to start asking questions now, and we'll get to those after the last speaker. I'm going to introduce the last speaker tonight, who is Ioana Colfescu, a senior research scientist at the University of Leeds, as well as an honorary fellow at the University of Edinburgh. She investigates the mechanisms of climate change using climate models as well as observational data. And she's interested in a range of topics, including extreme events, variability in Atlantic systems, and AI. Indeed, she'll be moving to Oxford soon to start work on AI applications in prediction of tropical climate change, which sounds fascinating. And again, in her free time, she participates in outreach events, hiking, taking photos, and telling everyone how fantastic her dog is. And I can tell you from what I've seen, her dog is indeed fantastic. Ioana, over to you.
Thank you very much. Thank you very much for the nice introduction. And thank you very much to SAGES for inviting me to give this talk. So my colleagues touched a bit on the uncertainty in the models. I'm going to get a bit into a bit more detail, and I'm going to give an example of what exactly this uncertainty means for a particular, let's say, topic in climate change, which is the Atlantic Ocean multidecadal variability. So you can see here, I'm introducing a notion which can look a bit like really mysterious science, Atlantic Ocean multidecadal variability. What is this? I'm going to start by introducing this. I don't think can you see my highlight here? Here it is. Yes. So basically what we call Atlantic multidecadal variability is a quantity which we use in climate a lot, and it is an index. And in the case of the Atlantic multidecadal variability, we have two elements that are part of the definition of this quantity. The first is a spatial pattern. So if you look here over the globe, we have a region over the Atlantic, so over all the Atlantic basin. And the surface temperature, which you can see here in color, so these are anomalies of the surface temperature in comparison to a long-term climatology. the surface temperature in this box, of course, varies. So if you think in general, probably in 1 year, this will be more negative. You can see here is, for example, if we look at the legend here is -1, in other years, it might be more positive, and so on and so forth. If we average all the surface temperature over this region, we get one number for every year, for every month, and so on. So basically what the second part of this pair of elements is a temporal variation, and I can't seem to make this work. Okay. So you can see here on the x-axis, as the time passes, as the years and months pass, the corresponding SST in the North Atlantic is changing. So you can see it becomes very warm in around the 1900s. It stays warm as we go forward in time for a longer period up to 1960s, and then it becomes cold again, and so on. So this oscillation in the Atlantic, that is a pair between the sea surface temperature variation, the spatial variation, and the temporal variation, is what we call the North Atlantic multidecadal variability. Why is this important? It is important because although it happens only in the Atlantic, it is linked to, it has remote effects. Like, for example, it affects central India, the central Indian precipitation, it affects the continental US, the rainfall flows, it affects the tropics, the precipitation in the Sahel, and so on. It also affects, and that is very important, the hurricane activity in the North Atlantic. And one of the main questions is, will the AMV get to a negative phase back again? Because right now we are in a positive phase. And it seems, of course, like just basic thinking that the more heat we have in the Atlantic, the more potential for hurricanes we have, although it's more complex. And this is an example of September 2020, when at the same time, we had only for the second time in history, 5 cyclones forming and 5 potentially big storms forming in the Atlantic. So this is associated with the extreme heat in the North Atlantic. And what we are interested in is, will we get a negative phase of the MV back again? How is this oscillation working? So what causes it, or what do we know? In terms of mechanisms, what do we know is that, so this plot here is quite complicated. You have to see that, so this is again the North Atlantic. You can see here the US, Africa, the same here. If you focus here first, so the main point that this plot wants to give is that we have an atmospheric component. We have a low and a high here. There is also an oceanic component. So of course, you know, the atmosphere and the ocean will interact. There is a current here that brings warm water. We have warm waters here. So the ocean does something, the atmosphere does something else. On the background of all this, we have a deep oceanic circulation, or the branch of a deep oceanic circulation that we know exists here. So this sea surface temperature will interact, the one that forms the index will interact with the atmosphere, as well as the deep oceanic circulation. And on the top of all this, we have external forcings, like, for example, volcanoes, and the most important, the man-made forcings, like the CO2. And the question is, how will this oscillation be affected by all the interplays of forcings, like how will the deep circulation affect this, and of course, how will our anthropogenic forcing will change or modulate this oscillation? So the take-home message for this is we have a very complex interaction, and disentangling all the factors and all the components is quite difficult. So what do we need in order to understand the uncertainty associated with this? So first of all, we need data. And here I'm going to just illustrate why previously my colleague said there is some uncertainty linked to data. This is a plot which shows, it's from a project, an ongoing project in the UK, and is a proposal for collecting data for the North Atlantic. And what you can see, there are, so these are different data measurements. You can see, for example, what we call Argo floats are like small data centers that are floating in the ocean, and they can gather information for various points. You can see we have, for example, an aircraft. So there was, the proposal was that, okay, we are going to fly along this yellow line and gather observation for the higher atmosphere. And then for the deep ocean, so if you imagine this would be like along the depth, for the deep ocean, we would have these devices. Some are fixed on the bottom of the ocean, so they would gather currents and temperatures, other are floating, and so on. So basically what you can see here is that we have areas, for example, where we don't have good curve coverage. So observations are not homogeneous. We have areas where if we want to measure the atmosphere, we will only take a profile along the line. What about the rest? Of course, we need observations for that. And then in the North Atlantic, so speaking about the deep oceanic circulation, which affects the sea surface temperature. So prior to 2004, we had only a few years of deep oceanic measurements. So this means that basically, and we try to look at an oscillation which is about 30 to 70 years with only a few years. So the message here is more data will be helpful in understanding the AMO, and we really need that. And the lack of data, of course, it's one source of uncertainty. The second source of uncertainty is, as Massimo showed and Andrew pointed out, it lays in the model differences. So different countries and different research centers run models to simulate different climate variables. And what you can see here is that index that I showed you before, the AMO. So this is the index evolution in time. The black curve is the observed sea surface temperature in the North Atlantic, so that average over the box. And then these are different models for different research centers. And the striking thing here is that we have periods, like for example, 1890s, where the models agree quite well. So they are all negative, although the observation seems to be more around zero, while there are other periods where the models completely disagree. If we look here, some particular models are completely out of sync with the observations. And of course, the question is, what can we trust and how can we trust the models, how much? Because of course, you wonder if this is for the past, so this is a reproduction of the past, how can we trust, or what can we trust for the future? So there is another source, and speaking about what can we trust for the future, the answer is we need to have a probabilistic approach. So this takes me to the third source of uncertainty, which is what was mentioned before, chaos or internal variability. Chaos is more linked to weather. So I'm going to start here by pointing out that when we look at the weather forecast, you see this notion here. This is, I think, from Met Office or the BBC. You see there is a chance of precipitation being smaller than 5%. So that means a probabilistic approach. It doesn't say the precipitation is going to be 3 millimeters or 4 millimeters. There is the notion of chance. So this chance actually is the thing under which we have the notion of chaos. The notion of chaos comes from the fact, so if you look here, assuming this is the temperature, so we would have here values 0, 1, 2, 3, and so on. And this would be day one, which we call an initial condition, and we want to do a forecast in time. So what happens is, assuming you take two trajectories that are very close together here, so let's say you have 1 and 1.1, so assuming we say, okay, we start with a temperature of 1 and 1 of 1.1, then we want to see what the forecast will be in few days. So basically what chaos means is that a small difference here will propagate into a huge difference later. So we start with a very tiny difference, and then one forecast might tell us, okay, we will have a negative temperature, and one forecast might say to us, okay, we will have a positive temperature. So that's why we need a probabilistic approach. And then we will say, looking at all these trajectories, we will group them and say, okay, there is a chance that there are 4 here. So the chance of the temperature to be in this range is this. The chance of it to be here is this. You can see there is a bigger probability, and then the chance to have a highly positive is here. This is an example of a forecast. This is a real forecast for temperature. So it's just to exemplify, this is a symbolic schematic, but just to exemplify a real forecast. So we start at day 0, so today, with a temperature around 11 degrees. And you can see as we advance, these are days, so day number 5, day number 10, this is what forecasters use. You can see that the range of these are different initial conditions or different models, like slightly different. And you can see, okay, this orange that comes from the different initial conditions becomes broader. And what started as, let's say at day 5, we have a small probability that, so we are going to be at day 5 between, let's say 10 and 15, 17. in this area, for example, by day 15 or so, we have a huge range of probability. And then as we advance, this huge range of probability stays. So this is what is called chaos. And the same concept is true for predicting other variables, like it propagates somehow to the AMO and AMV level. So going into that, this is a similar schematic to what I showed you before, but now for the AMV index. What this basically shows is if we want to look at the AMV simulated in models, so this is the same model, not different as they were before. What we call internal variability is the equivalent of chaos for weather, and it means if we start with slightly different initial conditions and we run the same model and the same simulations, we will have all this range. So the gray, the black curves represent the range of uncertainty. Usually what we trust is the curve in the middle, which is the average and is red here. And then the blue is the observation. So of course, if you compare the blue curve and the black curve, you can see there are areas where, for example, in around 1975, we have the blue here. So the AMO, the AMV was very negative, minus 0.4, whereas the models are centered more here, and they are the average of the model is quite positive. So this is the internal variability is something which it's a big source of uncertainty. And one of the main problems regarding the AMO in particular is, so how much of this oscillation, which we can study with models and then we can project, is caused by anthropogenic factors? So how much did we affect it versus this internal variability, which is a big cause of uncertainty. Basically, there are two camps, and this is almost my last slide. There are those who believe that the AMO is driven internally by this internal variability and by the ocean, and then those who believe that is basically radiatively forced by anthropogenic emissions and other aerosols. But this is an ongoing debate, is a big problem of research in climate science, and you can see why, because it's linked, it has remote effects, and it can affect many climate variables remotely. And there is, as Andrew presented and as Massimo pointed out too, there is also, regarding the future, there is another uncertainty which lays in the projections that we use for understanding this effect. So basically, when we want to look at the future, we use scenarios and we consider, for example, if we have a mild or a low emission scenario, this is the component of the ocean that is linked to AMO, you can see that this AMO, so this circulation, will basically decrease. While in the case of a very high scenario, so assuming we will continue to emit very, very intensely, then the AMO decrease will be much more sudden, and scenarios like in movies or in The Day After Tomorrow, or devastating effect on the global climate with stopping this circulation are going to come into picture. So yeah, I think that's it. This is my last slide.
Thank you very much, Joanna, and thank you very much to all of our panelists. So we've got a few minutes for questions. I've seen a couple coming in already. I'd like to invite all the panelists to turn on their screens. We might run a couple of minutes over. If we've got a few more questions, do type them into the box below. I just want to start with one. We've all talked about uncertainty. So how good can a model really be, and how much does uncertainty maybe affect policy? Shall I throw it over to Sabina first of all?
Oh, I think for the uncertainty, how much we can decrease it or not, I would ping that to the others. How much that impacts policy, I'm not an expert in that, but I do think that policymakers, that maybe scientists underestimate the degree to which policymakers are used to making decisions under uncertainty, also with other risks. And I do think we know quite a lot, actually. So it's certainly not a good idea to just wait and not do anything. I think we know enough for that.
Sure. So, Andrew, what do you think about the question of improving of the models?
Yes, I mean, it's a tricky problem. I mean, we're obviously getting improved. Obviously, the models are improving all the time. As Massimo showed, they're getting more and more complicated. They can simulate more and more things, which is very important for knowing what will happen to different aspects of the climate in the future. But unfortunately, they still are showing quite a lot of differences, and even the most basic thing, like how much will the world warm for a given amount of CO2. I think that I think that probably the best opportunity that exists in the future for this, and the best chance is as Massimo was saying, that the resolution of the model is incredibly important. At the moment, they can't resolve clouds. We are now getting to the point where we can run climate models on a very fine resolution. And I really think that that could lead to a big breakthrough. And for example, the Met Office's massive computer they're getting, I think could lead to some quite big improvements, in the not too long future. But maybe Massimo will want to say a bit more.
Well, Andrew, I agree with you. Resolution is an important aspect. I would stress the fact that observations are also important, and developing new understanding of how some processes are happening in reality and can be parameterized is also equally important. And we think here about aerosols and how they interact with clouds and how precipitation develops. Besides the increase of resolution and thus the possibility to go into cloud resolving modeling in global models, we also need to develop new understanding of some other processes. As I said, for example, aerosols is one.
Great. Thank you very much. I'm going to jump into a question we've had from the audience. So Belinda said she didn't see the nitrogen cycle represented in Massimo's description of the buildup of different models. And given that nitrous oxide is such a potent greenhouse gas, an anthropogenic disruption of the nitrogen cycle is just as serious as our disruption of the carbon cycle. Why is this? It's a question from someone who knows what they're talking about.
Yes, I can answer. But my answer is not really a direct answer, in the sense that is a simplified cartoon and which shows some of the key phases that were of development of climate models. Of course, the nitrogen cycle is one, but is here in the cartoon is hidden behind some development of actually moving from climate models to Earth system models and inclusion of biogeochemical cycles, fully interactive biogeochemical cycles, which I think is not in that cartoon, but we can say that with interactive vegetation and happened in the last 10, 15 years or so. So it's not there explicitly, it's there implicitly.
Great. Thank you. So we've talked a little bit about sort of the future predictions. We talked a lot about future predictions, but what sort of extreme events are we talking about that could happen in the future? We touched on a little bit about hurricanes, but what could happen specifically in Europe or in Scotland? What do we think that could look like? I'm going to throw that open. Joanna.
Yeah, I can take this one. So I think some reports regarding adaptation in Scotland say that basically the average temperatures will increase across all seasons. The weather will still be variable, will become a bit more variable than it is. So we can't say, I've seen someone who asked if Lanark will be a little bit more sunny. We can't say that. It will be variable. And then I think the winters are going to be milder and wetter, and we are going to have reduced snowfall and reduced frost. And I don't know if there is anything else. Probably the summers are going to be drier too. That's as far as I know. So if anyone else can add something else. And I had an addition actually regarding the improving in uncertainty. So there is a very big part of the climate community right now working on improving climate models and using methods of artificial intelligence and big data analysis, and that is emerging and is something that it's quite new, and we are trying in the climate community to basically take methodologies and statistical and artificial intelligence methods that have been used in other computationally heavy fields like biology or medicine, and apply it in our field to do better prediction and and understand processes better. So there is hope in that too. I think I have nothing else to add on this one.
Great. And so I realize we are running out of time. There's just one question I kind of want to finish on. Do you think from the modeling that's been done and what's going to happen in the future, there is cause for optimism, or does optimism not have a place when we're talking about climate modeling? More of a philosophical question.
I can say what I think. I think there's a lot of space for optimism. Plus, climate modeling, that's just a science bit, and that's a tool. And we've made massive progress in that. So there's a lot of optimism. It's a different question whether we're optimistic about climate change and such. But I think it's important to stay optimistic because we have still decisions to make now. And as I think all of us have shown, they impact what the future can look like. So just saying it's really bad anyway, that is not helpful, and we shouldn't do that.
Great. Thank you so much. And thank you so much to all of our panelists. I'm afraid we've run out of time for questions, but I'm sure that the chats can continue online on any social media channels. You can always put those in the chat after the talk. For now, I just want to say thank you. Thank you to everyone who's put this talk together, and thank you to all of our panelists for speaking and to all the audience for asking some questions. I want to remind you all watching to sign up to the mailing list about future events, which will appear in the chat. And I also want to remind you about our ongoing March SAGES Stories event. It's a competition called Water Wall in Motion. And everyone is invited to submit videos of how they use, how they monitor, or how they protect their local water resources. And there are apparently a range of exciting prizes available. I don't know what they are. Maybe I will enter and try and win one myself. Again, you can find more detail in the chat. The next event as well is in June. It's going to be all about the carbon cycle. And one more time, sign up to the mailing list if you want to find out more. So thank you so much, everyone, tonight. I hope you have a lovely evening, and we'll see you next time.